Welcome, everybody, to a special edition of Physics 230. Please provide a warm Davidson welcome to our guest, Dr. Bastani from Oklahoma State University. Dr. Bastani is going to teach us about single slit diffraction today. That is the first topic in chapter 36. And I'm not going to take, I don't want to take too much of her time, but I just want to remind you that we have a 30-minute quiz, online quiz, that is due today by midnight Eastern Daylight Time. So please do not forget to take the quiz. It should be relatively straightforward, and it covers the topics that are listed on our Moodle site. Are there any questions about the quiz before we proceed? Okay, I'm not seeing any. So if you have a question for Dr. Bastani, you can raise your hand. I'll be looking at the participant list, and I can help to keep her aware of any questions that we have in the classroom. We encourage questions, and you can also post questions in the chat if you would like to do it that way. And yeah, I have a private chat, which I will deal with later. Okay, so without further ado, Dr. Bastani.
Okay, good morning, everyone, and I'm glad to be teaching your class today. So let me go ahead and share my screen. Here. All righty, here we go. All right, now, what I want everyone to do as a wake-up exercise is to grab a paper and a pen. So if you don't have anything in front of you, please just go ahead and grab a piece of paper. So this is a wake-up call. And I want you to imagine that you have a monochromatic light passing through a circular opening like you see here. And then you have a screen in front of it. And I want you to imagine what you will see on the screen and draw it on the paper for me. Can you do that? So you have 1 minute to do that. So after you do it, please turn on your video, and if you feel comfortable, just show your drawing to class, or like to us. Just keep the paper in front of the screen. I want to see. Faculty can do it too. Feel free. So wake up exercise. So.
Anybody sharing?
Yeah, so I mean, it's not the most sophisticated drawing you'll ever see, but I think it's basically just like a larger, dimmer circle, right?
Let me see it again. Bring it up.
It's just a circle, but that's basically what I was thinking.
This is the first thing that comes to mind, of course. I just give you another minute because that was my surprise. Let me see. Oh, okay. Ethan, right? I like your drawing. Yes. Dan, Dr. Boy, is that what you see? Okay. Okay. Well, who else? I'm just looking at the... Okay. I have Parker, who is not awake yet. Carrie, Aiden, Taylor. Wake up, guys. Waiting for your drawings. Sena, is that how you pronounce it, Sena? Okay, so you see a circle there. Good, good.
Yeah, I also drew a circle, but I threw it out already, so.
Okay, hold on. I cannot see who you are. Okay, you are Tyler?
No, I'm Parker.
Parker.
Okay. So I didn't keep mine.
Oh, okay.
And that is Dr. Bastani, that is talar.
Talar. Okay. So, oh, okay. Because I use that. I see it. We use the same name in my country, and we call it talar, like right? Are you Armenian? Yes. Okay. That is what I guessed. All right. All right. Well, I think that is enough for now, but let's see what is the correct pattern that you see on the screen, okay? So if you have drawn something like this, and I saw one student had drawn it, I don't remember, unfortunately, the name. Who was it? Introduce yourself.
I just drew a circle with more circles in it. I don't know if
Yes.
that's like it.
And what was your name again?
Ethan?
Ethan, nice job, right? So this is the front view of the wave as the wave pattern, as you can see. And well, I mean, the first thing that comes to mind, and the first thing that came to my mind before I knew about diffraction was like similar to what you had drawn, many of you, just a circle, right? Because we have an opening here, so you just expect to have a bright circle here, but then you see that, wow, it's not what is happening. You see some dark and light fringes. So this is what we call diffraction. The diffraction of light passing through a circular opening produces circular interference fringes that often blur the image. Now, this is problematic when it comes to optical instruments. For example, to telescopes, right? Even the Hubble telescope suffers from the diffraction because then you get the blurry image. All right, so that opening doesn't need to necessarily be a circular one. You can have a slit. Even if you have a slit, then you will see a diffraction pattern, something like what you see here on the screen. And this is, of course, exaggerated, but you will see dark and light fringes with the one in the middle be the widest one. So we say that when monochromatic light strikes a single slit, diffraction from the edges produces an interference pattern that you see here. Okay, it was cool, huh? All right, now let's just spend a couple of minutes and take a look of why do we see interference and diffraction patterns. And I'm sure that this is something that you have been told before, but I'm going to review it. So light, as we all know, has aspects of both waves and particles. Now, the three models of the light that we're dealing with is the ray model, and this is what you see here. So in this model, light travels in a straight line. This is how we explain mirrors and lenses, how they work. The second model is the wave model, and that describes how light waves spread out and how superposition of multiple light waves causes interference, right? So the diffraction and interference is best being explained by the wave model. And the third model that we deal with in quantum physics is the photon model. All right. Now, what is the photon model? Now, what I want you to do, and faculty, please go ahead and do it if you would like. So go ahead, even if you want to Google it, you want to take a look at your book, if you want to privately chat with each other, feel free to. I give you 3 minutes to just throw some scientific guess. What is the photon model of light? Okay, what does this model exactly says? Just go ahead, take your time, 2 or 3 minutes. You can send me your answers in chat. I will check the chat. I think photons are particles of light. You think almost correctly, Dr. G. Okay, I haven't received any chat. Okay, now I see one. Force carrier of electromagnetic force. Photons are packets of energy that propagate like a wave. Okay. One more minute. Hurry up. Raise that energy. The photon model describes light collection. Okay, let me go ahead and read some of the answers that I received. Force carrier of electromagnetic force. Parker says photons are packets of energy that propagate like a wave. Then I have Julia that says the photon model describes light as a collection of particles called photons, no mass but contain energy. Correct. Then I have Gavin. I'm sorry if I'm pronouncing it not correctly. Says light waves are electromagnetic waves which are transverse, therefore causing interference when waves interact, right? And then I have Mason that says treating light as individual particles that move in waves. And then I have Ricky, particle of light that can be absorbed and released by other molecules. Talar, photons do not have rest mass, that is correct, but have kinetic energy, that is also correct. Although nowadays they are, no, that is right. That was, just disregard what I said. And then I have in photon model, rate of energy transfer of the wave is depending on number of photons arriving every second and energy of a single photon, and that is by Senna. It describes energy of light. And then I have another one from Talar. One photon can be absorbed by an atom or molecule, which results in the system being excited to a higher state. So all of these answers are correct. Now let's see. Okay, so the photon model says in the quantum world, light behaves like neither a wave nor a particle. Instead, light consists of photons that have both wave-like and particle-like properties. This is the quantum theory of light. And I'm sure that you're going to study more about it in future about quantum theory. But basically, in quantum theory, we say that photons have both wave-like and particle-like properties. Now, which one they exhibit when depends on the kind of interaction that they do. I just received another answer directly to its waves. Thanks, constant shows the energy to be. Well, thank you, Will. All right, now let's define now diffraction in the physics term, okay? So what is diffraction? Diffraction is the ability of a wave to spread out after passing through a small hole or going around a corner. The diffraction of light indicates that light is a wave, right? So this is one of the properties of the wave, diffraction. One interesting finding will be that a smaller hole causes more spreading. The smaller the hole is, you have the bigger spreading. Wow, so this is something now. All right, now diffraction and Huygens principle. So what you studied before was the Huygens principle. So I let you refresh your mind for a second, think about what Huygens principle was, and if it comes to mind, just send me a chat. Go ahead and send me a chat of what you learned about Huygens principle. Well, I guess the German pronunciation is Huygen, right? Huygens principle will, no, that is the previous answer. Okay. I see. Okay, so it seems that you have spent a good amount of time on Huygens principle, and I see nice answers here from Sam, Julia, Katie. Thank you, guys. Spencer, Dr. G, thank you. All right. Talar, of course. Will. All points on a wavefront act as isotropic source. Okay, so because I see that majority of you have remembered the Huygens principle, let me just go ahead. All right, so what Huygens principle says, just quickly, is that each point on a wavefront is the source of a spherical wavelet itself that spreads out at the wave speed. And then at a later time, the shape of the wavefront is the tangent line to the front of the, to all of the wavelets. Now, for example, when we have a plane wave, you can see that each point here is the source of a spherical wavelet. And then at a later time, the wavefront is tangent to all these wavelets. Now in a spherical wave, again, you see that each point is the source of spherical wavelet. And then at a later time, if I draw a tangent line to all the wavelets, then you get the later time wavefront. All right, now how is this related to diffraction now? So what happens here is that each element of area of the slit opening can be considered as a source of secondary waves. Now imagine dividing this slit into several narrow strips, right? Several narrow strips here. Okay, now, then this figure, the figure that you see on the right, shows two such strips. Okay, I just chose two of these strips. Now, the cylindrical secondary wavelets that you can see here are spread out from such strips. Now, if I want to show you this screen here on the right, shows that the intensity or the resultant intensity at a point P on the screen by adding the contributions from the individual wavelets. All right, now, this is called the near field diffraction or Fresnel. So the Fresnel diffraction is the near field diffraction, and that happens if the screen is close to the wave source. Okay, so when this happens, of course, we know that the rays that come from the wave source are not parallel. So the screen close is called near field diffraction or Fresnel. Now, what if the screen is far? So if the screen is far from the wave source, then that is called Fraunhofer or far field diffraction. So for having the image of the diffraction pattern in this type of diffraction, then you need something to be able to converge the wave rays that are initially parallel, right? So we can use a converging lens, for example, to converge these beams and then get the pattern on the screen. Okay, so two types of diffraction, Fraunhofer and Fresnel. Do you guys have any question? If you have a question, raise your hand or send me a chat. I do not see anything coming through. Okay. So before I start to work on the equations and the math behind the diffraction, I just go ahead and quickly give you a review of the double slit interference pattern. And this is what we need to know in order to understand diffraction better. Now, in double slit experiment, as you can see, we have a monochromatic light that comes from left, and the distance of separation between the two slits, I called it D. And then, of course, you have a screen in front of it. So the common sense would say that here is brighter, right? Like close to the middle of the screen, because there are two slits here, should be brighter. And then as you get far from this middle center, then you should have more dark area. So this is like the common sense. Even if you do not know anything about interference, what you would think is that you will have a lump here in front of this slit and another lump here in front of this slit. So anyhow, you will have like a bright region in the middle. And then as you get far from the center, then you will get like darker area. Now, hold on and stay with me. But then we defined interference pattern, and then we named this like middle bright fringe to be 0, and then the 1 and 2 and 3, like another constructive wave, and then here a constructive, interference, constructive interference, constructive interference. And then we know that the interference happens, and then you get like a bright fringe here, and then another one here, and then in the middle of them, you will have the dark fringes, okay? So this was everything that we learned about the double slit interference. And then if I define the distance between the wave's source and screen L, then we know that d sine theta is equal to m lambda, and lambda is an integer. So that was the equation that we got previously for the bright fringes in the double slit interference. Okay, so the simple geometry gave us this equation that the distance between the two consecutive light fringes can be written as L tangent theta, and then again L is this distance here, and theta is just like the angle between the center line and the first or the second, depending on the fringe that you want, light fringes. Okay, so that was a review to double slit interference. Now, It happens that when you have an opening, just a single opening or slit, well, again, like my common sense that I will see something bright here in the middle, and then I go farther away, and then I get dark spots. Now, what if I tell you that we will again see interference here, but this is self-interference. It seems that the light is self-interfering with itself. All right, so there is a joke that we do in physics classes, and we say that single slit diffraction is like getting surprised by a text you just sent yourself, right? So this is a self-interference. Now, let me see what does the chat says. Okay. Now, self-interference. Are you guys here? Are you guys just following the lecture? So we're this online capacity because I feel like a deep silence in class.
I think they're still there.
Yes, I can see some the names, but not the faces. Okay.
They can give you green check marks if they're paying attention.
Clap for me if you're paying attention. Clap, 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 clap. Or just show the reaction. Thank you, Aiden. Allison, I don't get anything. Oh, okay, perfect. Nice. Okay, now that I feel I exist and you exist, let's go ahead and continue this. So self-interference. Now, what I do is that I just go ahead and zoom in this slit here, okay? Let's just zoom in here. Now, what if I was to tell you that this slit is not actually one slit, but two slits? Who can just say no? I say that this is here two slits, not one slit. How? I just put a single dot here. Yay, and I made this into two slits. All right, so if I have one beam of light being passed through this edge and another one from this dot here, I can do that, right? So what happens is that, like we learned before, I can go ahead and find the difference of the path between these two beams. Now, if I draw the normal to this path, to this ray, then this small section here, this is width divided by 2 sine theta, right? So this is what you learned in the interference. So this is the difference. This is the W divided by 2, and then this small part here is W divided by 2 times sine theta, because this angle is here is a sine theta. Now, if the path difference happens to be equal to the wavelength divided by 2, or half of the wavelength, then light from these two strips arrive with a half cycle phase difference. Okay, so half cycle phase difference means cancellation of the wave, and yoo-hoo, we have a dark fringe. So if width divided by 2 sine theta is equal to half lambda, now we have dark fringe here. All right, so what I previously had for the double slit interference was that D, and the D was the separation between the two slits. Here, W is the width, was half lambda. Now I have W divided by 2 sine theta equals to half lambda. All righty, so let me just go ahead and get rid of the 2's in the denominator, and then I have W sine theta equals to lambda for my dark fringe. Okay, so it doesn't have to be only one ray, right? It can be the second ray. If like there is a second beam of light here, I will have another beam that will just interfere with it, a destructive interference. If I have the third one, there will be a third beam. If I have the fourth beam, there will be another beam. And this goes on and on and on. Now, what if I was to tell you that I have 4 slits? It's not 2 slits anymore, it's 4 slits. So I just can go ahead and put another 2 dots here and make that, or divide that 1 slit into 4 slits. Then I have the wavelength divided by 4 sine theta is equal to half of the wavelength for the dark fringe. And then what if I said it is 8 slits, it's 16 slits, it's 32 slits. So I can just go ahead and divide this just single slit here as many times as I want. So if I do that, so you see that for the 4 one, so this cancel with this, you get 2 here, and then for the next one you get 3, and then 4, and then 5, 6, 7. So general, you can write that W sine theta equals to M lambda for the dark fringe in the single slit diffraction. And this M can be plus and minus 1, plus and minus 2, plus and minus 3, and so on. All right, questions? Let me see, I have 2 chats. What does it mean that L is bigger than W? Nice question, Ethan. So it means that the distance between the screen and the source and the slit should be much bigger than the width of the slit. Okay, so if the width is like comparable to the distance between the slit and the screen, then that doesn't give us the diffraction, or we cannot say all these equations here. Did you get your answer? Okay, thanks. Okay. All right. Now, so now that I know that, let's go ahead and look at the diffraction pattern that maybe we can see it better now. Now, this is the bright light fringe in the middle, and you see that we do not have M equals to 0 anymore. So this is not like the single slit the double slit interference. So you have M equals to 1 for the first dark fringe, and then you have M equals to -1 for the one that is just symmetric with the other one. And then you have +2 here, -2, +3, -3, and so on. So let me show you here. W sine theta equals to M lambda. So I can just go ahead and solve that for sine theta and write it to be M lambda divided by W. So this is equation 36(2) in your book. Theta is the angle of line from the center of the slit. If the slit is here, imagine that the slit is here. So the angle between the center of slit to the mth dark fringe on screen, and then W is the slit width. And then what we know from math is that for the small angles theta, sine theta is almost equal to theta. And Ethan, this is probably another reason that we should have L much bigger than W, so that the thetas are small. So for small angles theta, and this theta should be in radians, pay attention to that, then I can write sine theta to be theta, and then I get the angles to be M lambda divided by W. And this let's call it equation number 2. Okay, so the last remaining equation that we want to drive here is that, just take a look at this picture here. Now, if I call Y to be the vertical distance of the mth dark band, and this point P here is the dark fringe from the center of the pattern, and L is the distance between the slit and the screen, and theta is of course this angle, then I can just use a simple geometry and write tangent theta equals to the opposite divided by adjacent. So tangent theta equals to Y divided by L, right? And then it happens that for small angles theta, not only sine theta is equal to theta, but tangent theta is also theta. So tangent theta is almost equals to theta 2. So I have now theta equals to y divided by L. From before, I had theta equals to m lambda divided by w. I just make these two equal, and I can get a nice equation for y in terms of m, w, and L.
Solmaz, we have a question.
Go ahead.
Oh, yes. Could you talk about like the specific ranges of angles? Because I know you said it has to be small angles. But is there like a specific range that for this equation to work?
Well, when I say small angles, so that is comparable. So by small angle, I mean something that the width, like when the width is like much, much smaller than the length. For example, we can have like 20 degrees, okay? Or all the way to 30 degrees, but we cannot have 45, 50, 60, 70, like 90. I mean, of course, 90 is just somewhere here. So I cannot give you the specific range for theta right now. So what is important for us is that like this length will be much bigger than the width. For example, if this is nanometer, then this can be in centimeter or like in meter, you know, like a whole different scale. Did that answer your question?
Yes, thank you so much. Appreciate it.
Of course. Any other question? No question. All right. So let me go ahead and compare now the double slit pattern with the single slit one, right? In the double slit pattern that we saw previously, so you have this nice like dark light, but then when it comes to single slit, you have this wide, bright fringe in the middle, and then you get two dark fringes and so on. So this is just a nice comparison to visualize the patterns. And of course, what physics course will be without solving an equation, right? And I see that I have still like 10 more minutes. So let me just solve an example for you, and then I let you do the second example yourself. Now in example number 1, I have a monochromatic light passes through a slit of width 1.75 times 10 to the power of -5 meters. If the first dark fringe of the resulting diffraction pattern is at angle 2.28 degree, what is the wavelength of the light? Now, did I tell that the small angle should be around 20? I made a mistake. It should be less than 5 degrees usually. So this is what we consider small. All right. Now, using this equation for the wavelength, W sine theta equals to m lambda for the wavelength. So it's just like a simple substitution, right? So I can solve this equation for lambda. And then I write lambda to be W sine theta divided by m. The width is given to us, 1.75 times 10 to the power of -5 meters. So they did even like a conversion for us. This is in SI unit. And then the angle is 2.28. And then m is the number of the fringe that we are looking at. Here it says the first dark fringe. Okay, so I just divided by 1, and then the wavelength is going to be 696 nanometers. Is that clear? If it is clear, clap for me. So those who didn't clap means that it is not clear, or it means that you're sleeping.
Maybe they are clapping on their picture instead of clapping on the participant.
Oh, I see.
I'm not sure. I don't have everybody's picture.
Okay. All right, now this is question number 1 for you, class. So it says, if the width of the slit through which light passes is reduced, does the central bright fringe become wider, become narrower, or remain the same size? Which of the following is the best explanation for your prediction? Okay, now you have 3 answers here, and then you have 4 choices here, and then let me go ahead and open this polling for you. Okay, so you can choose A, B, C, or D. One minute.
Dr. Bastani, I think we probably have about 20 students is my guess. So
Yeah,
if we get up in the high teens, so we have 16 responses right now.
okay.
We're pretty close to having most of the students responding.
And most of the students did wonderful. Okay, I just go ahead and 90-20. Perfect. So I have everyone answered me. All right, so end poll and then share results. I'm so proud of you. So I see like 74% said A, and that is awesome. Okay, go ahead. Now, answer. So what I'm using here is this equation that I had that gives me the relationship between Y and W, right? So the bigger the width is, the smaller the Y is. So the correct answer was number A, or the first answer. So clap for yourself now, those who got the right answer. Okay. Example number 2, light with a wavelength of 511 nanometers forms a diffraction pattern after passing through a single slit of width this much. Find the angle associated with the first and B with the second dark fringe above the central bright fringe. So M equals to 1, M equals to B. This is the first and second dark fringe above the central bright fringe. Now, if I want to picture problem here, I have a single slit, and then this is the central bright fringe, and I have M equals to 1, M equals to 2. Okay, let's go ahead and find the angle, right? So for that, I just have a simple equation. So the known of the problem is that I know the wavelength, I know the width, unknown theta. Now, I use the equation that I had for sine theta, and I just find theta to be sine inverse of m lambda divided by w, to just, again, substitute the correct numbers that you have. For the first dark fringe above the bright center, m is equal to 1. So if you replace it here, then you get the angle to be 13.4, and then for the second fringe, you just put m equals to 2, and then you get 27 degrees. All right, now, any question here? No question. Okay, so this is the question for you now. You pass 633 nanometers laser light through a narrow slit and observe the diffraction pattern on a screen 6 meters away, L equals to 6. The distance on the screen between the centers of the first minima on other side, so pay attention that this is the distance on the screen between the centers of the first minima on other side. So from here to here is 32 millimeters. How wide is the slit? Now you have 5 answers here, and let me start the poll. Okay, and hint, this is the equation that you're going to use. Well, we have 4 minutes, so just 3 minutes. So just 1 minute to solve this question. Okay. All right, so go ahead and just end this polling because I do not have that much time. So 60% of the class said C, or 60% of the students who answered, and then 27% A, and then I have some E. So let's see. So this is very straightforward problem. The only thing that you needed to pay attention to is that the distance that the book says or the problem says is 32 millimeters for like both sides. So you need to divide this by 2 to be able to get y for this equation. So here y is actually 16, here y is 16 millimeters, and then you need to convert the unit and just plug in into this equation, and you get 0.24 millimeters. So clap for those who answered C. All right, and I'm going to end the lesson now because my clock says 10:19, which is 9:19 in your time. Any question?
Talar has a question.
Go ahead.
Why is it 0.24 millimeters and not 24 millimeters?
Why I say point? You see, okay. Did you answer your own question or?
Yes.
Okay, okay. So
Sorry.
just make this 10 to the power of -3, and then you have to multiply it by another 10 to the power of -1. So write that 10 to the power of -1 brings this point to the left, so it becomes 0.424 millimeters.
Thank you.
You're welcome. Any other question?
It looks like that's it, Dr. Bastani. Can we stop sharing your screen just to wrap up the class? Okay. Excellent. Thank you very much.
Thank you, Sena.
Yes, if you appreciated Dr. Bastani's presentation, maybe you can clap on the participant screen, or you can clap on your picture. Thank you very much.
First.
So I have one more. Let's see. I have 2 announcements to make very quickly here. First of all, I was asked about accommodation on the quiz, and I will put those accommodations into the settings for the quiz. I'll do that after class today. I haven't done it yet, but I will take care of that if you have accommodation. And secondly, I just wanted to thank Dr. Bastani for introducing the concept of photons, because that's a topic that we will be getting into next week, actually. So I believe the lab next week will focus on light behaving in a photon way. And we will talk about that in class probably later in the week, next week. So that was a nice look forward to where we're headed in our class.
Well, I'm glad that you find it useful.
Yes, no, it was perfect, perfect timing. And yeah, we will be talking quite a bit about that picture, that model of light next week. So any final questions, or can we end the class? Okay, I think we're good. Thank you very much, Dr. Bastani. I'll see you in my office in a minute or two.
Okay, I see you then. I'm just
Bye,
like
everybody.
answering some of
Thank you for
the
coming to
chats.
class. Have a great weekend.
Bye,
Yeah,
everyone.